Welcome to Sans Summaries. I am Jamie Sands, and this is Further Algebra and Equations. So this is Sans Summaries, Further Algebra and Equations. Rational algebraic expressions. Introduction. A rational algebraic expression is a fraction that contains algebra. For example, x squared plus 3x plus 5 over x squared minus 2x plus 7. This is a rational algebraic expression. There's many things you can do. You can simplify them, you can add them, you can subtract them, multiply them and divide them. They are quotients, and hence we can do all the usual operations we would do on numerical quotients, which are just fractions. The next few slides we will explore these operations and techniques in detail. Simplifying rational expressions. To simplify a rational expression, we factorise the numerator and denominator and then cancel out common factors. For example, x plus 3 squared over x squared plus 7x plus 12. That factorises out as x plus 3 squared over x plus 4 times x plus 3, and we cancel out the x plus 3 in the bottom and one of the x plus 3's on the top, and it leaves us with x plus 3 over x plus 4. Multiplying rational expressions. To multiply rational expressions, we multiply the numerator and then multiply the denominators, and then we just simplify them. It's quite straightforward. So we have x plus 3 squared over x squared plus 7x plus 12 times x squared plus 8x plus 15 over x squared plus 7x plus 10. So we factorised the bottom of the left-hand fraction, and that gave us that expression there. We factorise it further using just your normal factorisation of quadratics, and it brings us down to x plus 3 squared times x plus 3 times x plus 5 over x plus 4 times x plus 3 times x plus 5 times x plus 2. And what we can do then is we can cancel out an x plus 3 and an x plus 5 from the top and bottom, and it leaves us with x plus 3 squared over x plus 4 times x plus 2, and that would be your final answer. Dividing rational expressions. So what happens when you divide a fraction is the exact same when you're dividing an algebraic fraction. So what you do is the one that you're dividing by, you flip it and just multiply it. So let's have a wee example. X plus 3 squared over x squared plus 7x plus 12 divided by x squared plus 8x plus 15 over x squared plus 7x plus 10. This then transforms into a multiplication by flipping the right hand side fraction. There's your expression for that. We then just follow through and multiply the numerators and denominators as in the last slide, and it simplifies further, factorising fully, and it brings you down to x plus 2 times x plus 2 over x plus 4. The Cartesian coordinate system and linear equations. Things are getting interesting. Cartesian coordinates in 2 dimensions. It's just your x and y axis, so you find where it is on the x and where it is on the y, and you put a wee point. And there's some plots pointed there for you, nicely. Plotting graphs using their equations. If we have an equation of a line, say y equals 3x plus 2, you need 2 points to plot a line, but we will start with the 5 points with x values from -2 to 2. So we make a table like so, and you can see all the x values on the left hand side, and then you have your middle column with y equals 3x plus 2. That calculates your y value and gives you the y coordinate of the equation. And there's your plot, y equals 3x plus 2, and as you can see, every point that we calculated actually lies on that straight line. Linear equations in one variable. A linear equation is one of the form ax plus b equals 0, where a and b are real numbers and a is non-zero. For example, we could use algebra to solve 6x plus 5 equals 35. So 6x plus 5 is 35. We subtract 5 from both sides, and that gives us 6x is equal to 30. We then divide both sides by 6, and that leaves us with x is equal to 5. Linear equations in one variable. We will now look at where the variable appears on both sides. Use algebra to solve. 6x plus 5 equals 35 plus 3x. And there's your, it simplifies down to x equals 10. All you do is you subtract 5 from both sides. You then subtract 3x from both sides, and it brings you down to 3x equals 30. You then divide both sides by 3, and that gives you x equals 10. The equation of a straight line. The gradient of a line. A straight line has the point-slope equation y equals mx plus c. The gradient of a straight line can be found using the formula m equals y2 minus y1 over x2 minus x1, and this is the slope. This means to find a line's gradient, we need to have at least 2 points that lie on that line. An example. Find the gradient of the line with points -2, -4, and -1, -1. So m is y2 minus y1 over x2 minus x1, and that simplifies down to 3. So the gradient of that line that lies on those points is 3. The y-intercept value. This is the c on the line, the y equals mx plus c. C is where it intercepts the y-axis. So we have our 2 points, we have our gradient, and we see that y is equal to 3x plus c. We use the point -1, -1 to substitute into the y equals 3x plus c because we're trying to solve for c. Y equals 3x plus c, that gives you -1 is equal to 3 times -1 plus c, and it simplifies down to c equals 2, giving you a final answer of y equals 3x plus 2, which is here, y equals 3x plus 2. The point-slope equation of a straight line. We have a general equation here, the general point-slope equation it is called, and the equation is y minus b equals m brackets x minus a. We need, as before, the gradient in the point, so we have m is 3 and the point -1, -1. Substitute it into that equation, rearrange, and it gives us y equals 3x plus 2 again. This is just the same equation that we found using the other method in the previous slides. Y equals mx plus c, of course. Parallel lines. Parallel lines will have equal gradients m, but different y-intercepts. So for 3 equations we could have the same gradient, but the different intercepts, which are 2, 0, and -2, like so. So we have y is a half x plus 2, y is a half x, and y is a half x minus 2. And as you can see, those lines lie parallel, but every value of c is different, but they do have the same gradient, which is what we were looking for. Perpendicular lines, or lines that are at right angles to each other. Lines that are at right angles to each other are governed by the equation m1 times m2 equals -1. So they can be perpendicular if and only if their gradient is multiplied to give -1. If we know the product of the gradients is -1, we can automatically say the lines are perpendicular. We have an example of perpendicular lines, y equals a half x plus 3 and y equals -2x. So we have m1 is a half, m2 is -2, m1 times m2 is indeed -1, and so the lines are indeed perpendicular, as you can see here. The lines are in fact perpendicular. Simultaneous equations. So we have a wee introduction here to simultaneous equations. In the case of perpendicular lines, or any two lines that intersect, we can find the point of intersection using a method known as simultaneous equations. There are 3 different methods. So we have the graphical method, the substitution method, and the elimination method. And we'll have a wee look at an example of each of these 3 methods. In the graphical method, you plot them and then read off the intersection. In the substitution, you rearrange one line and substitute it into the other. And then in the elimination method, you use algebraic manipulation and you eliminate one of the variables. So the graphical method. You're given the following 2 equations, y equals a half x and y equals -2x plus 5. We need to find the point of intersection using the graphical method. So we create a table, and then we let x equal 0 and x equal 1 so that we can have 2 points on to plot the line. We extend the lines far enough on our graph so that we can actually see where they intersect, and then you read off the point of intersection. So you're given the following 2 equations, find the point of intersection. There's your wee table there, it gives you 2 points for each line. You plot the first line, You plot the second line, and then you read off where it intercepts. And that's the graphical method in less than a minute. The substitution method. This is one of my favourite methods. So you have the two equations, the exact same as before. Using the method of substitution, we find the point of intersection. So if y equals a half x, this is just rearranging the first equation. We have 2y equals x. We substitute equation 1, which is now in the form x equals 2y, into equation 2. So y equals negative 2x plus 5 gives you y equals negative 2 times 2y plus 5. So y is equal to negative 4 plus 5. 5y equals 5. Y equals 1. So you have now found your y value. 2y equals x. So 1 is a half x. It means x is 2. So you've found the point of intersection as before as 2, 1. The elimination method. You have the two equations. It's the exact same equations as before. So we're going to use the elimination method here. So we multiply equation 1 by 4 and then add it to equation 2. 4y equals 2x plus y equals negative 2x plus 5. So we add those equations together and that gives us 5y equals 5 and that gives you y equals 1. You then substitute y equals 1 into one of the equations and rearrange and you get x equals 2. Thus you have the intersection once again, 2, 1. As you can see, the three methods have given us the exact same point of intersection. Quadratics. These are smiley faces. Their quadratics are polynomials of degree 2. They have the general form, ax squared plus bx plus c, where a is non-zero and a, b and c are real numbers. There are various methods for solving quadratics. We'll solve by factorisation, solve by completing the square, or solve using the quadratic formula. What do they look like? So the way I think of it is you have x squared and that's a positive in front of the x squared, so you'll have a smiley face. And if you have negative x squared, it's like a sad face. If you're negative, you're upset and you have a grumpy face. So below, there's your positive smiley face, and there's your negative frowning face. The discriminant. The discriminant tells you how many roots, and roots are just the solutions there are to a quadratic equation. The formula for the discriminant is for given a quadratic equation, ax squared plus bx plus c equals 0, b squared minus 4ac. That is the discriminant. So if b squared minus 4ac is greater than 0, you'll have two separate distinct real roots, which are just two solutions, like 1 point there and 1 point here. If the discriminant is equal to 0, you'll have one repeated real root, where the apex of the graph lies on the x-axis, and if it's less than 0, you don't have any real roots. Example. Calculate the discriminant for the following quadratic equations. X squared minus x minus 6 is 0. X squared plus 4x plus 4 is 0. And x squared plus 4 is 0. For equation 1, we have a is 1, b is negative 1, and c is negative 6. You calculate the rest. A equals 1, b equals 4, and c equals 4 for equation 2. And a equals 1, b equals 0, and c equals 4 for equation 3. As you can see, when you calculate the discriminant for the first equation, you end up with 25, which is greater than 0. So for that equation, you will have two distinct real roots. For the middle equation, it is exactly 0, so you will have one repeated real root. And then for the last one, it's less than 0, so you have no real roots at all. Solution by factorisation. We solve by factorisation. X squared minus x plus 6 is 0. You factorise it, and then x1 is 3 and x2 is negative 2. X squared minus 16 is 0. Factorising, you get x minus 4 times x plus 4 is 0, and that gives you solutions x1 is 4 and x2 is negative 4. Completing the square. To complete the square, we require that a equals 1. If it doesn't, we divide through by a to achieve that a is equal to 1. We then take our value b, we half it and square it to find a half b in brackets squared, and then we will both add and subtract this value on the left hand side so as to create a perfect square. We also move c to the right hand side of the equation, and then we apply the square root properties. Completing the square example. Solve by completing the square. X squared minus 3x minus 5 equals 0. So we have the equation. We take c over to the right hand side. That gives us x squared minus 3x equals 5. We then half the b, which is a negative 3. So we have plus negative 3 squared over 2 squared minus negative 3 squared over 2 squared. So you get x squared minus 3x plus 9 over 4 minus 9 over 4 equals 5. We keep positive 9 over 4 on the left, take the negative 9 over 4 to the right, and it simplifies down to x squared minus 3x plus 9 over 4 is equal to 29 over 4. And that's, once you factorise, you get x minus 3 over 2 squared is equal to 29 over 4. You then take the square roots on both sides. On the left hand side, you're only taking the positive square root. On the right hand side, you need both the positive and negative square root. So you have x minus 3 over 2 is equal to the square root plus or minus is equal to plus or minus the square root of 29 over 2. So x is equal to 3 over 2 plus or minus root 29 over 2. And there you go, there's your final two solutions. 3 over 2 plus root 29 over 2, or 3 over 2 minus root 29 over 2. And there's no need to calculate those values into a decimal form. Those are the exact values, and those would be accepted as solutions. So there's another example here, and the difference here is you don't have 1 in front of the x. So the first thing we're going to do is divide everything by 2. We'll take the 5 over to the right hand side, divide through by 2, you get x squared minus 4x equals 5 over 2. We have negative 4 and square it, so we have x squared minus 4x plus negative 2 squared minus negative 2 squared is equal to 5 over 2. We take the negative 5 over 2, we take the negative 4 over to the right hand side, and it becomes the positive 4. You then simplify further, it becomes x squared minus 4x plus 4 equals 13 over 4. So x minus 2 squared is 13 over 4. Taking the square roots again, simplifying further, and then you have your final two solutions. It's very, very straightforward. Using the quadratic formula. The quadratic formula states that for any equation of the form ax squared plus bx plus c is 0, where a is not 0 and a, b and c are real numbers, x1, 2 is equal to negative b plus or minus the square root of b squared minus 4ac all over 2a. And that's a very important formula. It doesn't matter what quadratic you have, you use that formula and you will get the roots. It's really, really useful in real life for financial situations because you're going to get decimal solutions. Quadratic formula example. Solve using the quadratic formula. X squared minus 3x plus 2 equals 0. So a is 1, b is negative 3, c is equal to. And then we just use the equation on the previous slide, substitute in our values, and it simplifies down to x1 is 2 and x2 is 1. Solving rational equations. So in this section, we'll go back to looking at rational equations like the quotients we discussed in 2.1. However, in this section, we'll go a step further and try and find the value for x. Solve the equation and state the excluded values of this expression up here. So all we do is we're going to factorise the right-hand side, the denominator of the right-hand side, and then we are going to say that we can't have x as negative 1 or 3. So we multiply throughout by x plus 1 times x minus 3. Put it on top, multiply through, cancel out the common factors, and that gives you a linear equation which is 5 times x minus 3 plus 1 times x plus 1 equal to negative 6. We rearrange this, and eventually you come down to x is equal to 4 over 3, but you still cannot have x equal to negative 1 or 3. Inequalities. An inequality will have one of the following forms. It will either be a less than or equal to b, a greater than or equal to b, a less than b, a greater than b, or a not equal to b. We use all the methods we've discussed so far to solve inequalities, and the key point here is if you multiply or divide by a negative number, you must reverse the sign, and you may be given restrictions on solutions. An example, solve x for the following two inequalities. 6x plus 4 is less than or equal to 10, and negative 2x plus 2 is greater than 4. So 6x plus 4 is less than or equal to 10. Subtracting 4 from both sides gives you 6x less than or equal to 6. And that simplifies to x is less than or equal to 1. Negative 2x plus 2 is greater than 4. negative 2x is greater than 2, x is less than 1 because you've divided through by negative 2. Topics for next time. Functions. We'll look at functional notation, domains and ranges, and composite functions. We'll look at graphs and transformations of graphs. We'll look at the inverse of a function. Absolute value function as well. So that's all our topics for next time. Thank you for watching.